Okay, so one of the things that Dalton wasn't quite correct in is, and I mentioned this before, stating that all atoms of a given element have the same mass. So different isotopes have different masses because they have different numbers of neutrons. But it's the number of protons that tells us which element this atom belongs to. So we can calculate an atomic mass, which is an average mass for each element. So, for example, chlorine has two different isotopes. They have different masses. But we almost never are dealing with just a couple of atoms. We're dealing with billions and billions of atoms. And it's not going to be all one kind or the other. It's this consistent mix of both of them. So the average mass is what's useful to us. The average mass is given on the periodic table below the element symbol. And these numbers are calculated according to the natural abundance of each of the isotopes. So chlorine is 75.77% chlorine 35 and 24.323% chlorine 37. So this is the mass of that isotope in atomic mass units. And notice that it is a little bit smaller, but extremely close to the mass number, right? So chlorine 35, the mass is 34.97. It's almost 35. Chlorine 37, the mass is super close to 37. If you're not given the masses of the isotopes, like in the worksheet, there's a question where you kind of have to, you can't do a strict calculation. You just kind of have to think about it and do some estimating. And that really bothers some students. I don't care for it myself. But so what do? They didn't give you the mass of the elements. Well, if you're just approximating, we can say, well, chlorine 35 is approximately 35 atomic mass units. That'll be close enough. So how do we calculate the average mass or the atomic mass? In everyday life, when we want an average, we take all the different numbers and we add them together and we divide by the total number of things, right? We can't do that here because there's not time in anyone's life to add all this up, even if you could identify how many of each of them you have. But unlike, say, taking an average age or an average weight of the class or something, here we have a limited number of choices, right? So for chlorine, there's only two things. So instead of adding 34.97 50 gazillion times and adding 36.97 20 gazillion times and dividing by 70 gazillion, we're going to use what's called a weighted average. So this percent means 75.77 out of 100. That's what percent means. Percent is literally per 100. 75.77 per 100. So that can be expressed as 0.7577. So we're going to take our percentage and express it in its decimal form. And we're going to multiply that by the isotope mass that has that abundance. So 75% is chlorine 35.7577 times the mass of that isotope. And that gives us a number. And chlorine 37.2423, because it's 24.23% times its mass, gives us a number. And then we add those together, and that gives us our average atomic mass. And it doesn't spend someone's lifetime to do. So let's look at an example. Magnesium has 3 naturally occurring isotopes. So they're giving us the masses and the abundances. So we've got 23, that's not what I wanted to do. 23.99. That's not what I wanted to do either. So the 23.99 is 78.99%. They're giving them in order. the 24.99 atomic mass units is 10%, and the 25.98 is 11.01%. That's what they mean when they say respectively. We're listing these things in the same order. So the first and the first, the middle and the middle, the last and the last go together. Calculate the atomic mass of magnesium. So what we're going to do is we're going to take the abundance, express it as a decimal, just divide by 100, and multiply by the mass. And we're going to do that for each of the isotopes and add them together. So 78.99% would be 0.7899 times the mass of that one plus 0.100, 10%, times the mass of the next one plus 0.1101% times 25.98. And then on your calculator, you can just do this. You don't need those parentheses. 0.7899 times 23.99 plus 0.1 times 24.99 plus 0.1101 times 25.98. .309099 atomic mass units. I encourage you to get your calculator out and do the calculation with me. That's why I don't have numbers written down, is to slow myself down so that you can do it along with me. The other thing is, if you do the math with me, then you can catch me when I make mistakes, because I do all the time, and I need you to catch me on those. So if I throw up a number here and you're like, that's not what I got, punch it through in your calculator again. If you still get the same different answer than I do, please raise your hand and tell me. Okay, what should we do about sig figs here? So the I hate sig figs method would be to look at what we're starting with. All of those have 4 sig figs and 2 decimal places. So it seems pretty reasonable that the answer is going to have 4 sig figs and 2 decimal places. And for this one, it ends up being exactly that. So 24.31 atomic mass units would be a good answer. This is an average of these numbers. The average has to be larger than the smallest and smaller than the largest, right? It's going to be in the middle somewhere. So if you do the math here and you end up with 75, 75 cannot possibly be the average of 24, 25, and 26, right? It's just not possible. That means I did something wrong. That's the red flag. Go back and look at what you did. You may have set it up incorrectly. You may have pushed buttons on your calculator wrong. You should always write out what you're doing, type it through on the calculator, write the answer down with at least 2 extra digits, and especially if it isn't reasonable, go back and do the calculation again. Especially on an exam, I encourage you to just clear your display, do the calculation again. If you get the same number, you probably did it correctly, or you're really good at making the same random mistake. Not likely. If you get a different answer, do it a 3rd time and go for best 2 out of 3, right? It was embarrassing last night in my Chem 1B class. I was being a little bit sloppy because I hadn't written it all down like that, and I was punching it through, and I swear I did that problem. This is not in front of the class, at least. I think I did it about 10 times and got 10 different answers because I kept screwing up because I didn't write it down. It would have been faster if I'd written it down. Any questions? So how do they figure out what the mass of these particles that are too small to see is? A great technique is called mass spectrometry. I'm not going to test you on this, but I just want you to know about some of these cool techniques. So this is a simple diagram of a mass spectrometer. So we get our sample and we inject it into the instrument, and we've got a heater here that'll turn whatever it is into a gas, right? So then the gas is going to come through here, and we've got an electron beam that is going to cause the atoms to have a charge on them. We want them to have a charge because then we can accelerate them and move them because of their electrical charge. So we can use electric fields to speed up those now ions and shoot them here into this magnetic field. Charged particles interact with a magnetic field, and so that's going to cause the stream of particles to bend. How far it bends is going to depend on how much those things weigh. If they are light particles, they will bend a lot, and if they're heavy particles, they will only bend a little bit. And then there's a detector here that identifies, how many particles are hitting. It gives us a signal. Any questions? So you end up with something that looks like this. It's going to give you an intensity percentage. So this one is the silver 107, and this is the silver 109. And so the tallest one is always going to be the 100%, and any others are going to be some lesser percent, because this is just telling us this is the highest. So the intensity of the peak tells us the relative abundance. The position of the peak gives us the mass. And then to calculate the average mass from this information, you have to normalize the intensity so that you get it equal to 100, because you can't have 90% of this and 92% of this. That adds up to more than 100, and so that doesn't work out. So this is how you normalize that. There is one homework question that asks you to do that. So you just follow this example. I'm not going to ask you about that again.